Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at a physics past paper question, and it's going to be covering Module 5 of Inquiry Question 3. In this problem, we're going to be looking at how objects are launched into space and at what height are they orbiting around a given planet, in this case, Earth. So, question 17, it says the diagram shows the position X on Earth's surface from which a satellite is to be launched into a geostationary orbit. Now, hopefully, before the point you get to this lesson, you would know what a geostationary orbit is. It is an orbit that goes around the equator of the planet, so it kind of orbits around the Earth's equator, and it takes about 24 hours to complete one whole orbit. So in many ways, you can actually say the geostationary orbit is traveling at the same speed the Earth is rotating around its axes. Let's have a look at what the question wants us to do regarding the following scenario. So in question A, it says, on the diagram, draw an arrow to show the direction of launch from X and justify your choice. So obviously there's only, well, I guess if you're really creative, there's a couple of choices, but there's only theoretically two options. We can either launch the object with the motion of the orbiting planet, or the rotating planet, or we can launch it in the opposite direction. Now, the correct answer is we have to launch it in the same direction. The reason being is the Earth is rotating in this particular orbit, or in this particular direction, and the object is being launched in the same direction. Then we can actually add on the speeds. It's almost as if you were, say if you were walking on an escalator and the escalator was going upwards and you're just standing there. If you're just standing there, the escalator will progressively take you further and further up. So technically, you're not actually stationary, you are moving. But if you were to start walking in the same direction as the escalator is moving, then you have your own speed plus the speed of the escalator. And that's what we're trying to do here. By launching in the same direction as the Earth rotates, we get an additional speed, and that makes it more fuel efficient, but it also means, we travel faster, we escape the Earth's gravity a lot faster without the necessity of additional fuel. So the reason why we want to launch it in the same direction, so launching in direction of Earth's rotational direction, will ensure it increases the initial speed of rocket, I think it was, satellite. Initial speed of satellite when launched. You could say it is to save fuel, but obviously it's just to justify your choice, 1 mark. So increases the initial speed of the satellite when launched. That'll be good enough for 1 mark. Question B, it says, and I'll change color to do this question. It says, given that the radius of Earth is 6.38 times 10 to the power 6, calculate the height of the satellite above the Earth's surface. Okay. So let's go through some information we probably do know. The formula we're going to be using here will be the Kepler's law, or third law, mixed with Newton's gravitational constants. What we're going to say is this value of R, we're going to say the value of R is the height, which we'll call X, plus the radius of Earth, which we can sort of rewrite it like so. So we're going to try and find the overall distance first, and then we're going to subtract the radius of the Earth to find the value of x. We already know what the mass of the Earth is. You can find this. As you can see, it's not on the question, but you can find it on the formula sheet, which is 6.0 times 10 to the power of 27, or 24, sorry, kg. And I know that the orbital period is 24 hours, but we need to convert this into seconds. So in 1 hour, there's 60 minutes, and in 1 minute, there is 60 seconds. And that'll be the total time passed. So that gives us 86,400 seconds. Okay, so what we need to do next is to rearrange this equation to have r as the subject of the equation. So I'm going to write r cubed equals to gm 4 pi squared multiplied by t squared. I am going to then substitute the values in first. So I know that big G is the gravitational constant, which I didn't write down, my apologies. The mass of the Earth divided by 4 pi squared, and then multiplied by the time squared. And we're still dealing with r cubed. I'm going to write that number down, and then we're going to cube the answer. So what I'm going to do is I'm going to cube root the answer that I found, which is 7.56736. Whoops, that's a 2. 3 times 10 to the power of 22. So when I cube that value, I get the following value here. 7523.87. So that's the distance covered by the height of the orbit and the orbit of the Earth. So the height that we're looking at is the value that we have here, subtracted by the Earth's radius. And let's see what we have here. We get 3591753.78 meters. I'm going to round this off, and I'm also going to try and put it in scientific notation. So the overall height, if we round it off to, in this case here, according to the lowest significant figures I use in my calculation, which is 2, I'm going to round it to 2 significant figures, so 3.6. So it would be, let's see how many decimals I have to move back by. 1, 2, 3, 4, 5, 6, 7 times 10 to the power of 7 meters. And that's how you solve the problem. Now, if you actually remember the exact value the orbit should be, it's around about 36,000 kilometers. So our answer that we have here directly matches what the answer would have been based on the slides that we talked about in the previous video. So that's how you solve the problem regarding the height of the satellite. If you found this video useful in breaking down the direction of launch and applying Kepler's third law to find the height of a satellite in orbit, like, subscribe, and we'll see you next time.